Right, this is a quick video on the relationship between Ka and Kb. So now we've learned Ka is the acid dissociation constant. We've learned Kb is the base dissociation constant. And what we don't know yet is that there is a relationship that exists between the two. So I have this bullet point that says consider NH4 plus and NH3, which are conjugate acid-base pair. So if we think about NH4 plus, we can think about that behaving like an acid because it has a H plus to donate. We could include water in this or we could not. So I think about it ionizing H plus NH3, all aqueous. And I could come over here and write the Ka expression for this, which would be H plus times NH3 over NH4 plus. And then I could think about how ammonia, which we've talked a lot about, behaves like a base when it reacts with water by taking a H plus from the water, leaving behind OH minus. And we can write a Kb expression for that. NH4 plus, OH minus over NH3, leaving out the water because we know it's a liquid and it is excluded from the equilibrium expression. Okay, so then if I think about these reactions and I think about adding them together, like kind of like a Hess's law lookalike problem, I noticed that my NH3s would cancel, and I also noticed that my NH4s would cancel, leaving me with H2O ionizing to give H plus and OH minus, and that should look familiar to you. That's the auto-ionization of water. Which we know is equal to something called Kw. Now, if you can remember back from equilibrium, we talked about when we added together equilibrium reactions similar to a Hess's law type discussion, we multiplied our two equilibrium constants together. Remember, it wasn't that we added them, we multiplied them. So technically we would multiply Ka times Kb, which would give you, if you really sit here and look at it, here's Ka, right, and here's Kb. Oh, I'm squeezing this in. Well, look what happens. H plus and OH minus, right, are left, which meets this expression for this reaction. And so what we come up with is, in fact, that Kw is equal to Ka times Kb. Kw we know is a constant at room temperature, 1 times 10 to the negative 14th. And so just like we equated Kw to H plus and OH minus, now we can equate Kw to Ka and Kb. If I know one, I can always find the other because I always know Kw. Let's do a couple bullet points and then we'll do a practice. Okay, so we know that the larger the Ka, the stronger the acid. And I'm going to now add a second statement onto this that says the larger the Ka, the stronger the acid. However, the stronger the acid, the weaker the conjugate base. I'm going to say Cb here for short. So, a large Ka for the acid gives a small Kb for the base. Lots of up-down arrows there, right? Can you see where we could be talking about that? The larger the Ka, the more it has ionized, so the stronger the acid, right? However, the other day we learned the stronger the acid, the weaker its conjugate base. So now we know if we have a strong acid with a big Ka, we have a conjugate base that's weak, which would give us a small Kb. And you have to think about it, Ka and Kb always equal the same number when you multiply them. So if my Ka was raised, if it got larger because it was a stronger acid, well then my Kb must decrease so that when multiplied together, they still equal Kw. All right, and then I have one more. I kind of ran out of room here. I'll squeeze it in. One more discussion on sometimes, just like we talk about changing H plus into pH and OH minus into POH, sometimes these values are expressed, or Ka and Kb can also do the same thing, where we look at the logarithmic function of Ka and Kb. And so we call these values, we can calculate something called the pKa of an acid, and it's negative log of the Ka. And we can calculate something called a pKb for a conjugate base, and it's equal to negative log of the Kb. These are going to come up later. So it's just a logarithmic function, right? Think about it. pH, negative log of the H plus. So pKa, negative log of the Ka. These formulas are also on your cheat sheet, and so they don't have to be memorized. Okay, so how could we use this? Well, it says calculate Kb for the fluoride ion F minus. Okay, so Kb, this is a base. F minus is a base. We know it's a base. It's the conjugate base of the weak acid HF. So I'm going to go to the chart and find Ka for HF. We're going to look it up. 6.8 times 10 to the negative fourth. And then we can say, well, I know Kw is Kb, or Ka times Kb. So I'm looking for Kb, divide both sides by Ka. Kw over Ka. Kw is 1 times 10 to the negative 14th. And Ka for HF, the acid, is 6.8 times 10 to the negative 4th. I divide these numbers. I get 1.5 times 10 to the negative 11th, right? And think about this. Ka for HF was 10 on the order of 10 to the negative 4th, so relatively large, and Kb then must be relatively small on the order of 10 to the negative 11th. So that is the relationship